Hello, today we'll be going over number 24 of the 2019 AMC 8. This problem in particular is quite interesting because even though it's an AMC 8 problem, it looks a lot like an AMC 10 problem. In future years, it wouldn't surprise me if this comes up as number 13 or 14 on the AMC 10, as this level of geometry is not really common in an AMC 8 test. Without further ado, let's get to it. In triangle ABC, point D divides sides AC so that AD and DC equals a 1:2 ratio. Let E be the midpoint of BD, and let F be the point of intersection of BC and AE. Given that the area of triangle ABC is 360, what is the area of EBF? Right now, we're trying to find the area of triangle EBF, but we don't really know anything about it. So let's label it as X. What do we know? We know that the area of triangle ABC is 360, and that will be probably crucial into finding the area of EBF, as the only other information we got is the 1:2 ratio between AD to DC. So if AD and DC are in a 1:2 ratio, that means if we label AD as X, or as A in this case, because we already have X there. If AD is A, that means DC must be 2A. One thing we can notice by looking at this triangle itself is that triangle ADB and triangle CDB both share the same height but different bases. And we know the ratio that their bases are in with one another. This can correlate to their area. The area of triangle CBD is also twice the area of triangle ABD. So using this information and that they sum up to 360, we can determine that the area of triangle ABD is 120, while the area of triangle BCD is 240. Going one step further with this, we can also see that the same thing we observed with the triangles ABD and BCD can also be observed with the triangles ABE and AED. Both these triangles share the same height, but unlike the other two triangles, they also share the same base. If two triangles share the same base and the same height, the area of a triangle is base times height over 2. So considering all these factors are the same, we can say that triangles ABE and AED have the same area. Since they have the same area, and both their areas combined equals to ABD, which we know is 120, we can say that triangles ABE and AED each have an area of 60, which we can draw directly into the diagram. From there, we notice that we have this huge quadrilateral region that we don't know anything about. In order to make this easier to deal with, we could probably turn it into a couple of triangles, as it's easier to find the area of a triangle than it is this irregular quadrilateral. So we draw auxiliary line EC. Then we notice the similar relationship that we've seen several times throughout this problem. Two triangles with the same height, but bases that are in the same proportion to one another. In this case, we notice that triangles AED and triangles EDC have the same height, but just like triangles ABD and BDC, one of the bases is twice the others. This means that one of the areas is exactly twice the others. Since we know that triangle AED is equal to 60, we know that the area of triangle ECD is 120 because it's supposed to be exactly twice the area because their bases are twice as much. So then we write in area of triangle EDC is 120. That leaves us with one final area in our triangle. The area of the triangle, as it tells us the problem, is 360. So far, adding up all the areas, we get the areas of our known parts to be 240 plus x, with our unknown part being the area of triangle EFC. In order for it to be 360, whatever EFC has to equal has to help bring this up to 360. And after subtracting 240 plus x from both sides, we see that triangle EFC must be equal to 120 minus x. So now that we know all these areas, we can kind of do what the reverse we did to get said areas. To get these areas, we compared the bases and created areas based off those. But now, using these areas, we can create relationships between the bases. So let's look at the area of x, because anyways, that's what we're trying to solve in the grand scheme of things, because x represents the area of our unknown region, EBF. So there's several lines we could hunt for in terms of x, but it seems that EF is probably the best line to compare. And since EF is on the same line as AE, it seems like it's a good idea to compare these two with one another. So then, if we set up the relationship between EF and AE, what can we say? Well, we see that triangle BEF and BEA both share these lines as bases, but they also share the same height. So whatever the ratio between the bases are, it also is the relationship between the areas. So since we said that the relationship between the bases EF and A is EF over AE, since they share the same height, we can also say that the areas are also in the same relationship. So we get that EF over AE is equal to x over 60. Now if we flip over to the other side of AE and EF, we can see the similar kind of thing happening on the other side. Triangles ACE and triangles ECF both have the same area, but their bases are in the same ratio as EF to AE. So we can write their areas in the same kind of way. We can write 120 minus x is over 180 is equal to EF over AE, which is equal to x over 60. With that, we get a relationship in terms of x, which we can solve in order to find the value of x, and thus find the area of EBF. So, if we cross multiply these two parts, we get 180x is equal to 7200 minus 60x. Then, if we bring all the x to the same side, we get 240x is equal to 7200. Divide by 240 on both sides, we get x is equal to 30. And as I've said earlier, x is the area of EBF. So, since we know the area of EBF is 30, that is the right answer. Thus, the answer is B.